Today's section is about power series again. Okay, the functions represent the power series. It's more precise. We're talking about functions represented by the power series. Okay. Before we discuss the general theory, I'm going to just go back to the function again. Okay, so here's a function. We're nowhere, right? It's very. So this is a function defined on the whole line except for when. But how to express it as a power series? A power series must be in the form, in this form, okay? A could be any point, okay? So this is a coordinate line, okay? This is a function, and here's a one. So graph of this function is when x is power greater than 1, I think it's below the axis. When x is greater than 1, less than 1, this is going like that. This is a point 1. When x equals 0, the value is 1. So this is a function, okay? Of course, you cannot express the power function as a power function to 1. But for any number which is not equal to 1, you can always find the interval, okay? The largest possible interval you can get is this one, because the other side touches the 1, right? So this is a R. Over that interval, you can always express it as a power function, okay? So over the interval, this particular function can be expressed as a power function, okay? And you can tell what is A here. A is going to be absolute value for 1 minus A. It depends on its greater than radius R, okay? So for any x in this interval, okay, for any x in this interval, you can express the function as a power series, okay? For this power series, if x is greater than, if x is greater than 1, no, if x is outside this interval we're talking about, then this power series will be divergent, okay? But the function is still defined. So this is the interval, okay? So if x is not in this interval, the right-hand side power series you get is going to be divergent, okay? And I forgot the expression. In my last lecture notes, you can see the Cn, okay? We already defined out. But the special case is what happens at A equals 0, it's origin. And this is, we know that's geometric series. So we know that f of x equals 1 minus x. This is going to be x to the power n. And this is going to be 1. And this is r, right? So for x between negative and positive 1, okay, both sides are equal, okay? And if you look at the geometry series, this series is divergent for x outside 1, or even for x greater than or equal to 1. So this is a divergent for x greater than or equal to 1, okay? This is a note. All right, but the function on the left-hand side is the one is defined for any x not equal to 1. Okay, that just match over the interval. So let's understand that first, okay? And actually, the general formula, this general formula at the arbitrary value a1 not equal to 1 is obtained by this special one, okay? So as in a good exercise, let's look at this function. This is going to be x plus 3, okay? Now, this function is not defined when x equals -3, okay? clearly the domain of this function is going to be x. X is not going to be -3, right? So for any number away from -3, I should able to find this is a -3. So any number which is not in -3, I should able to find the interval on which I get a power series around that, right? So for example, you can choose x equal to 0, okay? Or you can, how about this, right? So for this interval, over that interval, okay, I is going to be 3, right? So I'm able to find out, and x is -3, so just x to the n, okay? Right, so question is, over the interval from -3 to power 3, okay, I'm able to express it as a power series. Okay, let's do it. Okay, how can I do it? Well, I use the above formula, but then you have to modify it, okay? So x plus 3, I have to make it look like the above one, okay? I take 3 out, I get 1 plus x over 3. Great, sounds good, right? It's very close to 1 over 1 minus x. I still needed to change it to 1 minus something, okay? So then this complete look like the above one, 1 over 1 minus x, okay? So using the above formula, it's going to be negative x over 3 to the power n, as long as negative x3 this is less than 1, okay? Then you modify and you get negative 1 to the power n. You see? Okay, this inequality is less than 3. Yeah, the same. Okay, those two are the same. Okay, it's done. So coefficients, you can move 3 inside. So this is my CN. So 1 of x plus 3 can be expressed as power series, right? For x less than absolute less of x less than 3. Okay, and it's done. You just all I have to do is just always, express it in the form like 1 over 1 minus x. And similarly, you get like a 1 plus x squared, right? How to express it? Express it in the form. Okay, I can do that. But maybe not easy to get it to an arbitrary point. I'm not sure you can do that, okay? Like how about the x at the 1? Okay, this is maybe it's easy. Maybe we can do that, but not right now. All right, so let's look at this, right? You still express it in the form 1 minus negative x squared, right? So this is in the form like 1 minus, 1 minus u equals, right? This holds for u absolute u less than 1. So you have to express in that form. Then, okay, then you get x. And this holds when negative x squared is less than 1. But this is the same as absolute x less than 1, okay? All right, so now we get that means the other term all gone, the even term left. So this is power series, okay? If you really have to express it in the form like that, k equals 0, c to the k, x to the power k, then what you can get? Well, when k equals 2n, right, it's negative n, right? when k equals to n, n starts from 0, so plus 1, then this is going to be 0. You can say that. Okay. When k is even, when k is odd. All right. Right, so now let's take a look at a function. Those are the element function. We know the function we know. We just find the power series representation. But in general, not every function is represented by power series. Is the element function. Okay, so we can we consider this power series. Okay, and first thing we have to make sure where it can be defined. Okay. We know that if Cn plus 1 over Cn has a limit, okay, then you can show that, but this is not necessarily always, okay? So we know that if this limit, okay, equals L exists, okay, or okay, then it happens because this is not a whole, this is just series, right? There's x minus 1 there. So that implies right equals L times x minus a. Okay, and this also implies equals L x minus a. Then you can tell when it's convergent, when it's divergent. Okay. Then you can say that then the series is convergent. The power series, okay, not just series. It's it's absolute convergent. If L times x minus a is less than 1. Otherwise, it's divergent if L times x minus a greater than 1. So it's important. What is L? L could be infinity. Okay? L could be finite. Yeah. So L x minus a less than 1 is the same as x minus a less than 1 over L. Okay? It's the same. In some extreme case, for example, if L is 0, if L is 0, this really means x minus a is less than infinity, okay? Yeah, if L is infinity, this means, this really means, we just assume that that's our assumption, okay? Because 1 over infinity is going to be 0. Okay, that's a too extreme case. Just be careful, okay? Yeah, because the series will be convergent only when x equals 8. Right? You know this. Okay. The series is convergent only when x minus a is 0. Okay. Right, so this is how do we get the radius? It's called the radius of convergence. So this interesting is power series. Okay. If it's convergent, it'll be convergent for all x in some interval. It's not like, oh, here convergent, then divergent, convergent, divergent. It's like, the x value. So if you look at, if you look at the set of the x for which it's convergent, the set of x usually occupy the whole interval. Okay, accumulate. Yeah, this is a phenomenon. Okay, so this is a, and here's a minus r, a plus r. Okay, so we don't know the end point, but the set of x for which the power series convergent, okay, is usually the interval, maybe including endpoints, possibly including endpoints, right? So, but this is for at least for this kind of a power series, when the limit exists, okay, when the limit exists, see, we under this assumption, we get that, right? So we see that this series, okay, for this series, the set of x for which it is convergent, not necessarily absolute convergent. Okay, it's convergent is an interval. Okay, it must be in the interval. Okay, but possibly including with a center A. Okay, but possibly including the endpoints. Okay, because we're talking set of all x. We only know in the interval it's convergent, also interval it's divergent. Maybe at the endpoints like absolute condition convergent, absolute, we don't know. Okay, but this phenomena is also true even the limit of Cn. This is what I want to say, that this is actually true for arbitrary power series. It's not necessary for the Cn, with the limit from the ratio test exists. Okay, so this is true in general. Okay, so we have the following theorem. For an arbitrary series, okay, and there's a number, okay, that number we call it r, the radius, okay. There's number equals 0 of positive finite or infinity, okay, such that when, okay, the series is convergent, it is absolute convergent actually. Okay, for x satisfying the Cn code, okay, and divergent for x satisfying x minus a greater than now, okay, and but we don't know the endpoint. We don't care about that. case by case way to do this. Okay. Because it's convergent, okay? So we let f of x to be this. Okay. Okay, this is defined for x let. Okay. Second, we find out this function you define is always differentiable. Not only differentiable, but the derivative can be obtained by the series. Okay. This is still true for x less than r. Okay. More important, this indicates for the power series on the right hand side. Okay. Has the same radius convergence as the original. Okay. Second, this series is going to be the derivative of the function, which is defined by original series. Okay. So the power series, I'm sorry. Okay. This power series, okay, this power series has same radius of convergence. Okay, you're not going to get that power series after you differentiate each term. You're not going to get worse power series. It's possible worse a little bit, but we don't have the end point. Okay, inside, and it is absolute convergent to the derivative, absolute convergent, not just convergent. Okay, absolute convergent is the same power series, same radius convergence. Okay, but it's possible the end point power series may be divergent, but original one is convergent. Okay, it's possible. Only the end points get worse when x equals, and when x minus a equals plus minus r, that's possible the original power series convergent, but condition convergent, the new power series is divergent. It's possible. We don't care about it. Third, the integral of this function exists. It's going to be right, and then plus constant. Okay, this still holds when x minus a less than r. Okay, and this power series still have the same radius of convergence. That means this power series is not going to have a larger radius convergence. So if you use a power series to define a function, and just like a polynomial, you can freely find the derivative. You cannot express it by elementary function in many cases, but it's so convenient to find the derivative, find the evaluate integral. All you have to do is do it on each individual term. Okay, you're not going to modify the power series, but you're not going to change the radius convergence. That's interesting. Okay. Okay. So let's take a look at the example. This is my favorite example. First of all, I know this power series, okay, is convergent to a function, and we're lucky the function is 1 of x. Okay, that's for x less than 1. So the radius of convergence is 1. Okay. Over the interval from -1 to +1. Okay, this power series is convergent, absolute convergent. It is convergent to a function. That function actually is 1 over 1 minus x. That's understands its logic. Okay. And so now we can differentiate, right? In the interval, we can differentiate both sides because they're equal. We can integrate. We're not going to change the radius convergence on the left-hand side. Okay, we differentiate. When you differentiate, when differentiate nx to the n minus 1. And the derivative on the left-hand side, I think it's 1 minus x to the negative. When you differentiate, you get a negative sign. So actually it's 1 minus x squared. Okay, the negative sign is gone. So you can rewrite this again. You can rewrite it again. You will get start from 1 n minus 1. So start from 0. K plus 1 x to the power k. You can write this form. Okay, you let the k to be n minus 1. Yeah, actually n start from 1 because here n is 0, then it's 0. First term is 0. Anyway, you can rewrite this again. So this one, right? So this power series is also, okay, this power series has same radius convergence. You can prove that directly. Okay, the radius of convergence of this new power series is going to be still 1. Okay, and you can prove that directly without using the above theorem, because k plus 1, when you use the root test, when you use the ratio test, does not contribute anything in the limit. Okay, it's always convergent to 1. So just look at this. Yeah. So k plus 1, without k plus 1, k plus 1 doesn't matter. The radius of convergence will be the same. Okay. If I just give you a function like that, it's harder to tell. This is going to be 1 over 1 minus x squared. Okay. So actually, this function also this power function also represents an elementary function, which is 1 over 1 minus x squared. Okay. And this is divergent. It is divergent if absolute x is greater than 1. We don't care about the end point. Okay. We ignore the end, the interval. Okay. But 1 over 1 minus x squared still defined for x equal to 10. Okay, because this side is defined for all x except for x equals 1, right? So, but that only match over the interval from -1 to positive. Then we it again. Okay. All right. So now we continue. We integrate. We get x to the n plus 1 over n plus 1, which is going to be integrate 1 minus x squared dx. Okay. So entire derivative will be, I think, not only just natural log. We assume x is smaller than is close to, because x is between negative and positive. So 1 minus x positive, but there should be negative sign in front of that. Okay, because when you differentiate, you got negative sign. All right, and the plus another constant, because both sides are indefinite integral, right? So let's assume this is true. So you have to determine the coefficients constant c. So what happens when let x to be 0? So c equals natural log, right? 1, which is 0. Okay, so c is 0. So in other words, I get natural log of 1 minus x is going to be negative. Okay, the leading term is going to be negative x plus x squared over 2 plus x cubed over 3, and so on. Aha. So if x equals 1, this is a harmonic series that's divergent. X equals 1, left hand side is natural log of 0, which is right. Okay. Anyway, so this is it's interesting series. So natural log of 1 minus x can be expressed as power series, but this is true for x less than 1. Okay, when x absolute x greater than 1, this side is divergent, but this side, when x is less than negative 1, it's defined. Okay, so this side is divergent for x greater than 1. Okay, but this side, interesting, is defined for x greater than 0, so it's less than 1. Okay, but x could be negative 10, negative 20. Okay. So what do we get here? Yeah, this is as a graph. All right, so we can also move the negative sign to the left-hand side. Let's draw the graph, okay? When x equals 1, that's 1. So the function for the natural log, it's defined on the left-hand side. When x equals 0, it's passing through the origin, okay? So what I'm going to get here, this is going to be 1 minus negative x, okay? So for x, positive, I think this is a graph. Okay, this is a graph, okay? This is a graph y equals negative natural log of 1 minus x. Okay. Right? So what we did here is, over that interval, we find a power series representation for the function over that interval. Okay. When x equals negative 1, okay, when x equals negative 1, what I get? When x equals negative 1, negative 1 the left-hand side, left-hand side is still convergent, okay? So series but this holds only for absolute x is less than 1. But if you let x approaches negative 1, and you probably get very interesting result. X equals negative 1, right? When x equals negative 1, okay, the left-hand side is going to be negative natural log of 2. If this is true, we don't know. You have to verify that. Okay, so this is a question. Okay. That's a good question, right? Because this above equality only hold. We only know that it's less than 1. This holds. Okay, I did not say this holds for x equals negative. So that's the reason I'm going to ask you this question. And if it's equal to what? Okay. All right, so this is important identity. And let's continue. Now, to find the power series, right, representation for some, let's go back to elemental function. Okay. The function here is given 5 minus x. Okay. So this function is defined when x equals 1 or 2 or 3, any number, right? This is a defined for x less than 5, right? It's always defined for x less than 5. So any number less than 5, at any number, can I find power series representation? Okay. Okay. My question is, I want to express it as some power series. I pick up a number, 4, 3, 2, 1. Doesn't matter, right? Let's say 1. Okay. And I even can tell the rate of convergence, because if you look at the graph, right? This is a 1, this is a 5, right? When x is getting close to, when x is getting close to 5, this is getting negative. When x equals 0, nature log of 5. So the graph looks like that, okay? Yeah, this is a value, nature log of 5, positive. Okay. Where's the 1? 1 is here. So I'm going to, the maximum interval I can get is this piece. Okay, what is the radius of convergence? 4. Okay, this point would be -3. Okay, so I think I'm able to find power series representation for the for that function over the interval -3 to 5. The radius of convergence is 4. How to do that? Well, we're going to use known result. Okay, I know. Okay, here's a fact we already get. Natural log of 1 of x is negative. N starts from 0, n plus 1, x to the n plus 1 for this. Okay, as long as absolute x is less than 1. So I'm going to express 5 minus x in that form. But I have to expand it around the 1, not around the 0. So I'm going to let and u to be x minus 1. How about like that? Okay. All right. So this is idea. 5 minus x, x is going to be u plus 1. Cool. Right. So simplifying it, I get natural log of 4 minus u. Okay, the 4 shows up here, right? But that's not good enough yet. I have to express in the form like this form. Okay. So how can I do? I take the 4 out. Okay, which is going to be natural log of 4 plus natural log of 1 minus u over 4. Now I'm in the form natural log of 1 minus something. Okay, and then according to the above identity, it's going to be n plus 1 u over 4 to the n plus 1. And this holds when u over 4 is less than 1. Okay, this holds. Okay. We just use above fact. So let's rewrite in another form. Natural okay, and u to the n plus 1 is u is x minus 1. Okay, absolute of u less than 4 means x minus 1 less than 4. See, this is a radius convergence given also the same height. That's it. Maybe you can rewrite again because you don't like, n starts from 0, but actually n plus 1 start from 1. K start from 1. K times 4 to the power k. X minus 1 to the k. That's better. When k equals 0, the coefficient is going to be the x log of 4. Okay? So k start from what? Because when k equals 0, 1 over k times 4 to the k is 0. So it's undefined. Okay. But so this is identity, right? We solve the problem. Okay, and this holds when x minus 1 is less than 4. This is natural log of 5 minus x. So in other words, you can approximate natural log of 5 minus x by this power series. You can choose sufficient large n. You can look at partial sum. Okay. So we have an arbitrary function here, and look at this function where it is defined. I think when it's defined, when x is going to be, yes, the domain of this function is all the x, 2x plus 3 cannot be 0, right? So all the x cannot be negative 3 over 2. Okay. So you take an arbitrary point which is not negative 3 over 2, and you're trying to find the power series nearby that point. So here is the interval, right? So this is 0, here's negative 3 over 2. So if I choose this number for my power series, then the largest interval I can get is this, because the function is not defined as negative 0 over 2. So let's try to express it in this form. So here x is less than r. So what is r? I think r is going to be 3 over 2. I know r before I even solve the problem. You look at the picture. Because the largest interval you're going to get with the center 0 is going to be the interval with radius 3 over 2. Right? Otherwise, even the function is not defined when x equals 0. How can you say that equal, right? All right, how can I do this? I need the fact. It's going to be x to the n. Okay, this holds for x absolute x less than 1. So I'm going to modify the function into the form 1 over 1 minus something. Then use this formula. So those are the elementary functions. We're just trying to express it by power function. I just told you that power functions define many more functions. Okay. if compare this way. If all the elementary functions form a galaxy of our galaxy, the Milky Way, then all those functions represented by power functions, all the galaxies in the universe. Okay, it's a lot. Okay. All right, so yeah, using this fact. So I'm going to modify that. I let no, I don't need, yeah, I don't need that, not necessary. Because this is a power series around at 0 origin. So I take 3 out, I get 1 plus 2x over 3. It's pretty close, right? I need a 1. I need a 1 minus something in the denominator. That's why I take 3 out. Then I need a 1 minus something, right? So now everything's okay. So use the formula. You will get, right, sigma here from n from start from 0 and negative 2x over 3 to the power n. But this holds when this is less than 1. Okay. All right, so let's simplify. Can you try to simplify this? This inequality can change it to 3 over 2, right? Over 3. But this one, you have to express it in the form that then looks like a power series you need. Okay, of course you have to move the constant into okay. So those are the coefficients you're looking for. That's the CN. Okay. If I just give you this power series, can you recover the elementary function? Sometimes you can. Okay, but I can modify a little bit. Okay. Yeah, if you modify the coefficients, like I remove yeah, like a 3 to the power n, I change it to 3, right? Maybe it's still okay. I change it to the n. Maybe it's okay, right? So let's go to that way. So I'm given the power series. Okay, I'm going to change it to, okay, look at this, right? N starts from 1, not from, yeah. Okay. Am I able to, the question is, this is a power series, okay? So what is the radius of convergence? You can check. The radius of convergence is going to be 1/2, okay? So I told you that there are the series, the functions represented by power series are so many, they're different. Just like they occupy the whole universe, okay? But those the elementary functions are very small group. Okay. All right. So first of all, let's look at the radius of convergence. Okay. So this is the nth root. If you find the radius convergence, you can do all together. Okay, which is going to be, I think this is nth root of n. It's 2 over 3x. Okay, so the limit is just 2 times x. Okay, clearly it's convergent when this is less than 1. So the radius convergence will be right. So it is absolutely convergent if absolute x is less than 1/2. Divergent if absolute x is greater than 1/2. So I equals 1/2 is the radius of convergence. Okay. I don't know whether it's convergent at another endpoint. Okay. This is a 2n. Okay. So I let f of x to be this. Okay. And actually, this one is convergent on the no. This is not convergent at endpoint. Maybe no, it's convergent at one of the endpoints. Okay. So yeah, in fact, it's convergent when x is going to be yeah. Oh, don't. I'm going to let me finish that part before I define the function. So there's another concept called interval of convergence. Interval of convergence is going to be the set of all x for which all convergence. But right now we have an open interval, right? How about in order to find the interval convergence, I think it's going to be -1/2 and the +1/2. Okay, why -1/2 is included? Okay, when x equals -1/2, okay, 2x is going to be -1. Okay, the series. Okay, becomes, okay, so this is a convergent. That's the reason -1/2 is included. Okay, this series is convergent at the end of points, but it's not convergent when it's 1/2. In that case, the power series is going to be 1/n. This is divergent. So yes, this series, first of all, it's absolute convergent for x between -1/2 +1/2, right? And all sides away from this, it's divergent. But how about the endpoint? At the one endpoint, it is condition convergent. At another point, it is divergent always. Okay. But so this is the interval of convergence. Can we? So is it the elementary function or not? We defined power, right? So we let f of x equals okay for x. We just assume that on this open interval because we don't care about the endpoints. Okay. Is it elementary? In other words, does it represent an elementary function? The functions we're familiar with. Okay. If it is, what elementary function is represented by that? Right? That's the inverse problem. Sometimes you solve differential equations, and the equation, you solve it using power series. You determine all the coefficients, you end up with this. All right, so now right, how to do that? Well, at least over this interval, I'm going to put, the reason I cannot figure, it's difficult for me is there's n in the denominator, right? So in this interval, what I can do, I can freely differentiate both as a function defined by this power series differentiable. So I can differentiate. So what I get is just 2 to the n, x to the n minus 1. Great, right? Okay. I differentiate every term I get, but the derivative is easy to understand. So you can take 2 out. Okay. So n start from 1, then n minus 1 start from 0. So I'm pretty sure this is a k start from 0 to x to the power k. And we already know that this is going to be 1 over 1 minus 2x. And for x less than 1/2. Okay. So you get a function like that. I tried to see if f of x is an elementary function, but I know the derivative is. So what are you going to do? So that it's going to be just the entire derivative. Okay. I integrate. If I integrate, what is the antiderivative of this? I think it's a negative nature log of 1 minus 2x. Okay. When you differentiate, you get 2 in the numerator. Okay, a negative 2. So plus constant. So this is my x. I needed to determine the coefficient. When I look at the original function, what is the value function? When x equals 0, this is 0. Yeah. F is 0. So this implies c is 0. So now I get this answer. Okay. So yes, the function the power series I just gave to you, it's convergent. Not only convergent, it is convergent to that particular function. It is an elementary function. Okay. Okay, let's take a look at another series. This is n factorial x to the power n. So n factorial, 0 factorial is assumed it's 1. 1 factorial is 1. 2 factorial is 1 times 2, 2. 3 factorial is 1 times 2 times 3, which is 6. Okay? So this is our notation. So in other words, this is going to be 1 plus x squared over 2, x cubed over 3 factorial, and so on. Okay? Let's look at this series. First of all, let's look at the rate of convergence. Because this series, if it's convergent, right, it gives you a function. So, because it's involved n factorial, what test we should use? Ratio test, load test, comparison test? Ratio test, yes. Okay, so you look at this, you can see there's a limit n plus 1 factorial x to the n plus 1, and this is x to the n factorial. Okay, so now you get n factorial n plus 1 factorial, and here x to the n plus 1, x to the n. Okay, don't forget the absolute value, because that's what's stated in the ratio test. Okay, now after you simplify it, you will get 1 over n plus 1, but you have to get x. And no matter what the value of x you choose, because the denominator is n plus 1. So the limit is always equal to 0, which is always less than 1. So this power series, okay, is so special. It is convergent for any x. Okay, so this series is convergent for any value of x. So now we get a function f of x, which is defined by this power series. Okay, this is a function. Another question is it an element function? If it is, what is that? Right? Is it an element function? What function it is? Right? Yeah. Can we understand that, right? But this function is so special. Okay, it's defined, right? It's defined. We get a function for any x. I don't know at the very beginning what kind of function it is, but I wish to understand a little bit more about this area of the function. Right? I try to integrate, I can differentiate. So this function defined this power series is differentiable, and for any x. So when I differentiate, I get n here x to the n minus 1. So let me change it to n equals 1, n equals 0 can be ignored. So n starts from 1. Okay. Then I can let k to be n minus 1. So k will start from 0 again. K plus 1, k plus 1 factorial, x to the power k. Whoa, k plus 1 over k plus 1 factorial can be simplified to k factorial. What I find out is, no matter how they differentiate, I end up with the same function. So this function I just introduced as a power series. This function defined as power series is so special. It's derivative itself, right? Itself. Okay, no matter how many times differentiate, you always end up with the same function. There's only one function in the world has this property. That is the exponential function. Okay, this must be the power. Yeah, it must be e to the x because there's only one function. It has this property. It has this property. Now I cannot jump to conclusion right now, but let me show you how to do it. Okay, why? Right? Let's put it this way. Let y to be f of x, right? Then dy over dx equals f prime x, which is e to the x, which is still y. Okay, this is the way we how to solve differential equation. Okay, so here's the magic. Okay, dy over dx can be viewed as dy differential, right? Okay, that is going to be y dx. Cool. That's y over dy equals dx. Okay, then you put the integral. Okay, then you what? This is natural log of y. Okay, then what? Okay, and it is going to be e to the c, e to the x, some constant. Okay, so y should be plus minus that constant. Let's put it this way. Okay, so this is a function. It's not a unit. Okay? It must be the function like that. Any function in this form has a property. Its derivative is going to be itself. Okay, so y must be e to the x because depends on the initial value. So that means, okay, that means sigma, then I should use another capital K here. Sigma x to the n of n factorial is going to be k e to the x, okay? But when x equals 0, k should be 1. At x equals 0, that's 1 equals k e to the 0. So k is 1. So that's how do we get the identity. All right. So the exponential function is represented by this power series. Okay. All right. So some power series, some function defined by power series are still elementary. Like this. How do I find out? Because I find the derivative. I find the derivative is going to be itself. Then it must be in that form. Then I have to determine constant, and the step x could be 0, and both sides should match. So the constant k should be equal to 1. So that's why I have decided exponential function is a nice process representation. Okay, and it's true for all x. It's not like the function 1 over 1 minus x. So far we have a 2 identity right now, right? But the solving differential equations, it's not a trivial. Look like that. It's maybe harder to understand. How do we play with this? Okay. Yeah, we solved it using Math 266. Many students in engineering, especially electronic engineering, they have to take this course. 266 differential equations, and you will learn lots of tricks to solve differential equations. Okay, differential equation means it's inverse problem. You know some unknown functions, their derivatives, okay, satisfy some equations, then you have to recover it, solve it, find it. Okay, the simplest equation will be this, like this. The derivative of some variable is going to be itself, and what is that? That depends on, yeah. Then you can solve it in this. So that begin with this example in that particular course. Okay, I'm stop here.